Hello, this is Mr. Gilmore with the 7.0 Simplifying Radical Expressions lesson. Now, in this semester, we're going to be experiencing a lot more algebraic expressions. In particular, some of those that we're going to be experiencing are some of those that involve radicals, in other words, square roots. So what we're going to do today is actually brush up a little bit on our algebra of how to simplify our radical expressions. We're going to see a few properties that we are allowed to use with radicals, and then we'll actually practice simplifying at the very end. So what does it mean to have a simplified radical form? Well, there's three things that go into having a simplified radical form. The first thing is that no number under the radical has a perfect square factor, meaning we'll be talking about what perfect squares are here in a little bit, and also looking at how we can actually take a radicand, which is the number underneath the radical, and break it up into factors such that they might be a perfect square in there. Second thing that is not allowed in order for us to have a simplified radical form, is that no fraction is allowed under the radical as well. And we're going to learn how can we then fix that? How are we going to use properties of radicals to then remove any fraction? And the last thing that we're not allowed to have is that no radical is found in a denominator. So if we find that their square root is in the denominator, we're going to need to fix that, called rationalization. And we'll talk about that here in a moment as well. So what are perfect squares? Well, you've experienced perfect squares actually a lot. There are numbers that are greater than 1, and they start with the number 4, 9, 16, 25, and they continue on. If you notice what these are actually our integer values squared, right? 4 is really 2 squared, and 9 is really 3 squared, and 16 is really 4 squared, and 25 is really 5 squared, and so on and so on and so on and so on. And so we continue the pattern, right? 6 squared is 36, 7 squared is 49, 8 squared is 64. Now, why are we talking about this? Why are we talking about perfect squares? Because when we take the square root of a perfect square, it results in an integer value, a whole number. For example, if I come over to this very last number, 144, and I take the square root of that number, 144, being a perfect square, gives me a nice integer value. And so we're looking for perfect squares because that's going to actually help us simplify our radicals today. So a couple rules going into radicals before we begin into some of our own examples. When we simplify radicals, we actually have a couple of different rules. The first one is called a product rule. What a product rule says is simply that if we were to have a product inside of our radical, we can take that radical and break it up into two separate products, or two separate factors, meaning that in our example below, we have the square root of a times b. Both of the factors are underneath the radical. We're allowed to then separate that into the square root of a times the square root of b. And what that's going to allow us to do is when we find those perfect square factors, we can actually remove them from inside the radical and end up with some nice integer values on the outside. Well, there's also a quotient rule that goes into this. Quotient rule is saying that if we were to have a division in the interior of our radical, let's say we have this fraction a over b. In other words, it's a divided by b. Whenever we have a division property going on between two factors inside of a radical, we again are allowed to separate that single radical into two individual radicals, one for each of the division property or division numbers going on inside there. So in our example, we have the square root of a divided by b, but that's the same as actually saying the square root of a divided by the square root of b. And we'll look at how we can use that later on in this lesson to actually simplify a radical when we arrive there. Now, of course, the last thing is not really a rule. It just goes into the definition of what it really means to be fully simplified, and that is we're not allowed to have a radical in the denominator. So how do we fix that? We use this big fancy term called rationalization. Essentially what that means is we're going to multiply the denominator by itself. And when we do that, when we multiply by itself, it will actually cancel out the radical, right? Because if we were to do the square root of b squared, we would end up with just b, right? It actually simplifies that radical, giving us what that value of our denominator is. And we'll talk about how we can do that in an example here later on. So let's actually start with a first example of applying our simple product rule to actually reduce or simplify this radical. So we're going to simplify the square root of 48. Now the thing about the number 48 is that there is actually a perfect square factor going on inside there. Well, part of our rules for simplifying radicals says that we're not allowed to have any perfect square factors, which means we need to remove that perfect square factor. So the first question is, what is the perfect square factor that goes into 48? Well, I'm going to bring our number down here and say the very first thing I think of is what's the largest perfect square that fits into 48. The largest perfect square is actually 16. 16 times 3. So if we do 16 times 3, it gives us 48. But what we're allowed to do then is use our product rule. And our product rule is going to help us take that 16 out of the radical. So what this looks like is, right, product rule says, well, we have a product of two things going on there, 16 and 3. What we can do is separate that into two individuals radicals. So we have the square root of 16 times the square root of 3. What I can do that with that is square root of 16 is a very nice number because 16 is a perfect square. And we're going to be doing our perfect square hunting in order to help simplify our radicals. So the square root of 16 is 4. Now the square root of 3, well, 3 is not a perfect square, which means we are going to leave it in the radical. We're not going to touch a calculator. And what we end up with then is 4 radical 3. And that is the simplified version of our square root of 48. Now, you may have been asking yourself, well, I didn't know that 16 was the greatest perfect square. I did see that maybe 4 divides into it, and yes, 4 is a perfect square that divides into it. So what do we do when we don't know the greatest perfect square? Let's take a look at an example with that. So let's say I give you a number. Let's say down here at the bottom, we've got the square root of 450. And you're thinking to yourself, well, I really don't know what the greatest perfect square that goes into 450. But I do know there is one, and that the number is 25. Yeah, 25 goes into 450 evenly, and 25 is a perfect square. So what we can do is take this step by step to actually arrive to our goal. We don't have to pull out the largest, but we will continue to pull out perfect square factors until there are none left. So what I can do with this guy here is I break it up into 25 times 18. 25 times 18 brings us back to 450, but 25 being a perfect square, I can separate those using our product rule. So I take the square root of 25, and we've got 5, but then we have this square root of 18 left over with. So what our next question is there another perfect square factor that goes into 18? And there is 9, right? 9 times 2. So we didn't realize what the largest perfect square was just yet. What we're doing is pulling out all the perfect square factors that we can possibly find, even if we don't know what the largest one is at the given start of our example. So what we can do is then take the square root of 18, simplify that, and what we're going to do is just take the product of everything at the very end. So that 5 that we just pulled out, it's going to come along for the ride. So we just have 5 out the front, but then we can separate our 9 times 2 into the square root of 9 times the square root of 2. Now the square root of 9 does turn into 3. And again, this is still all being multiplied together. So they're all factors. It's all being multiplied together. So I'm going to do 15 times 3, and 5 times 3 and get 15. And then that square root of 2 I'm stick on the very end. So there's our simplified form. So what does that really mean for us? That means that we didn't find the largest perfect square, but we continue to pull out smaller perfect squares until there were none left. There are no more perfect squares inside of 2. I should say no other perfect square is greater than 1 inside of the number 2. So if you're not sure what the greatest perfect square is, don't panic. Just find one of them. Maybe it's 4, maybe it's 16, something small, and then you pull that number out and then continue simplifying. And yes, you may use a calculator to help you find those perfect square factors, but don't actually use a calculator at the very end. You're going to leave your answer in exact form, 15 times the square root of 2. Okay, let's do another example. Now we want to simplify the square root of 18 over 4. Now here's the tricky part. Look, it's actually, we've got a fraction inside the radical. And that's one of the rules about simplifying, simplest form is we're not allowed to have a fraction on the inside of the radical. So we got to fix this. Our very first fix is applying the quotient rule. This says that if we have a fraction, we may separate it into the numerator and into the denominator. So our fraction then turns into this. And that is going to help us simplify this even quicker because our denominator is really nice to us. When the denominator is not nice to us, we'll talk about that here in a little bit. But when the denominator is nice to us, it makes this our job a little bit easier to simplify because the denominator is a square root of a perfect square. So the square root of 4 is 2, and then I'm going to simplify the square of the numerator. I'm going to apply the product rule because inside the numerator, there's a perfect square of 18. 9 times 2 is 18. So what I can do is take the square root of 9 times the square root of 2, separate those, and then continue simplifying. So I leave my denominator just as it is, didn't change anything, but the square root of 9 is 3 times the square root of 2 in the numerator, all divided by 2. Now, that is our final answer. But a lot of times, students will make this mistake. Let me show them a common mistake. They'll take this root 2 over 2, and they'll go, oh, look, the 2's cancel out. Turn it into 1. The square root of 1 is just 1. That is incorrect. Okay? If there's a number on the outside and a number on the inside of the radical, they cannot actually interact with each other. Inside can interact with inside, and outside can interact with outside, but they cannot interact between inside and outside. So just don't make that mistake. So that's our final answer, 3 root 2 over 2. Let's do some follow-up questions before we conclude with talking about another thing we can do with radicals, which is called simplifying like terms. So let's actually simplify both of these using our rules. So I'm looking at number 1. We've got this 6 times the square root of 200. And you're probably wondering, what's going on with that 6 on the outside? Well, it's just given to us in the expression. So whenever we're working with our simplifying it, we're just going to leave 6 right where it is, and you'll see how 6 actually works its way into the solution here in just a second. So I have 6 times the square root of 200. I'm thinking to myself, what are two numbers that fit into 200? one of them being a perfect square. And I see, oh, that's actually very simple. 100 times 2. 100 is a perfect square. So I can use my product rule to separate it into a square root of 100 times the square root of 2, and then I can simplify that even further. So 100, square root of 100 is 10, and square root of 2. So now what we can do is finish that off. 6 times 10 is 60, and that's where the 6 kind of works its way back in, and then my root 2 gets just stuck on the very end. So there's my final answer. I can multiply numbers on the outside together, I can multiply numbers on the inside together, but I can't multiply outside and inside together. So there we have it. Now we're going to look at this last example here on this page. This is one where we're going to apply our quotient rule first, and this is where things get a little bit tricky. When I simplify the numerator, I just get 1, right? Square root of 1 is 1. But I can simplify my denominator, which means I'm breaking one of the simplest form rules, and that is I'm not allowed to have a radical in the denominator. How do we fix this? We simply multiply the denominator by itself. When we do that, it will help cancel out the radical. So what we get in the numerator is very simple, right? 1 times root 3 is just root 3. But my denominator, root 3 times root 3, what we really get is using our product rule, we multiply the insides together. So 3 times 3 is 9, and hey, look, we can simplify that. So we get root 3 over the square root of 9 is 3. And now we have finished our simplifying. It fits all the things. There's no more perfect squares on the inside of the radical. There's no fractions inside the radical, and the denominator does not have a radical in it as well. So there we have it in simplest form, simplifying those two examples. Now, this last little part involves actually the other operations we can apply with radicals. We talked about product rule and quotient rule, but there's also adding and subtracting. When we add and subtract radicals, it's actually just like when we add variables. We think of the two words like terms. So when the two values have the same number in the radical, then they are like terms. So for example, in the top example, we have 2 root 14 minus 3 root 14. Well, that means they have the same number in the radical. Those are like terms. We can actually simplify that. So 2 root 14 minus 3 root 14, the way I think about it is like this: 2x minus 3x. I can simplify that. I get negative 1x, which means my answer to simplifying that top one is actually just working with the coefficients on the outside. So 2 and 3. I'm going to do 2 minus 3. That gives me negative 1. And then what's my radical? Root 14. Now, technically, I don't need that 1 on the outside. So my answer is just going to be negative root 14. Okay. Now, you may be thinking, we're not allowed to take the square root of negative. And you're right. The negative's on the outside, so we're safe. But let's look at the second example below. Negative 5 root 7 plus 2 root 5. Are those like terms? Well, they're not. The numbers on the inside of the radicals are not the same. This would be like me saying negative 5x plus 2y. With the variables not being the same, that means I can't actually add or subtract those terms together. So in this case, what is this equal to? Well, it's already simplified. I can't simplify that any further. There's nothing else I can do with those two. So my answer is just simply leaving it like that. And that bothers a lot of students. But I still have operations. Yes, but it's in an exact form. You're not going to touch a calculator. You're not going to punch those numbers into. You're not going to give me any decimals. You're going to give me the exact answers also, which means you're going to leave the radicals in your answer. Now be careful. Sometimes you run into a situation like this, and the first reaction is going, oh, look, the numbers on the inside, they aren't the same, which means I can't add them. Okay, move on. All right, you're right, already simplified. But the thing is, we have to also ask this question before we get add and subtract. We have to ask the question, can we simplify these two? Does 45 and 80 actually have any perfect squares that fit into them? And they do. Let's start with the number 45 here. I can take the square root of 45 and break it up into 9 times 5. 9 being a perfect square, which means I can take the square root of 9, take the square root of 5, right? Break it up with the product rule, and simplify that. Root 9 is 3 times root 5. Now let's do that. So that's the simplified form of the first term. Let's see what happens if I simplify this last term. Let's simplify root 80. Root 80 has a perfect square into it, 16 times 5. So I can then take the square root of 16 and the square root of 5, and simplify root 16 is 4, and then we have root 5, and take a look now at the radicals. They are like terms. They each have the radical 5. So if I'm adding these, 3 root 5 plus 4 root 5, I end up with 7 root 5. I'm adding the numbers on the outside. And so there you have it. So be careful. Just because they have different numbers on the inside to begin with, the first question is to ask ourselves, can they be simplified? And if they can, do that. And then look for like terms. Look for whether you can add or subtract the two terms together. So let's do a little bit of practice towards for our last slide here. So in our first example here, root 9 plus root 25, well, both of those simplify. Root 9 is 3, root 25 is 5. So we're simply then just adding 3 plus 5. That is 8. That's a nice little simplification. Let's do our second one. Those are like terms. Look at that. 6 root 2 minus 10 root 2. Okay, that means I can add and subtract those. So I'm subtracting the numbers on the outside. 6 minus 10 gives me a negative 4 root 2. Okay, negative 4 root 2. So I'm working with the numbers on the outside. Those are like terms. The last one's going, they're different numbers. Move on. Well, no. We have to ask ourselves, can we simplify them? So let's first simplify 2 root 8. 2 root 8 actually does simplify. Root 8 does have a perfect square in it, 4 times 2. So it looks like this. 2 root 4 times 2. We're going to simplify that one. And the second term also has a perfect square in it. Root 32, we can actually simplify that one. 32 has 16 times 2. Looky there. So I'm going to go ahead and save us some time here. The root 4 here turns into 2, and then we still have a root 2 stuck on the inside. Over here we have the 4 on the outside. Root 16 is 4, and then we have the root 2, which is still stuck on the inside. So we end up with 4 root 2, right? 2 times 2, those numbers on the outside work together. And then 4 times 4 is 16 root 2. We can add those together. We get 20 root 2, and there's our final answer. So we've come to the end of our first lesson, 7.0, brushing up on some of our algebra concepts from previous years. If you do have any questions on this lesson, please be sure to ask. You have a homework assignment, 7.0, and if you do have any questions on that, please do not hesitate to ask me or email me. Get in touch with me. With that, be good and do good.